In this lesson, we're going to quickly talk about the idea of extrema. So I have here two graphs, and we're going to talk about two different possibilities for different types of functions. So just to have a name to give them, let's call the example on the left f of x. So here's our x-axis, here's our y-axis, and of course you remember when we're talking about graphs of functions, the inputs live along the x-axis and the outputs live along the y-axis. And then for our second example, let's call this function g of x. And again, here's our x-axis, and here's our y-axis. So we're going to do two things in this lesson. The first is define what I'm talking about when I'm talking about local extrema and global extrema. And then afterwards, we will actually look at the specific functions and identify where, if anywhere, these functions have these things. So the word extrema is just a catch-all that means either maximum or minimum. So, local extrema. I'm not going to make this definition super technical because actually you could, if you wanted, get really technical with the word local, but we're going to be very kind of informal about it. So there's the idea of a local maximum value and the idea of a local minimum, right? So extrema just kind of puts those two things into one category, but when you're talking about local extrema, you're talking about local maxes and local mins. So f of x has a local maximum at a if f of a is the largest value f of x attains around a. Okay, so essentially we're saying that you've got a local maximum if you can identify a little window around which f of a is the largest value the function attains. So one good example of this is something like a high school basketball program, right? So there can be many different high schools in a given city, especially if it's a big city. There can be lots and lots of high schools. But realistically, every one of those high schools might have the highest scoring player on their basketball team. So you could take the highest scoring player out of every single basketball team on every high school, and within the locality of the high school, that is the best basketball player. That doesn't mean that they're the best high school basketball player in the entire city. It certainly doesn't mean they're the best basketball player even in the county or in the state, but in that locality of the high school, they are the best basketball player. Okay, so that's a really good analogy. In fact, when you start thinking about sports, you realize that the analogy of local max and local min values become really easy to understand. They're very intuitive. Local minimum, exactly the same. So I'll just say here, same idea as local maximum. Just smallest value. So if you continue to think about the sports analogy, if you took every high school in a given area that has a track team and you looked at the person who ran the fastest mile, right? The smallest time to run a mile. Well, within that high school's track team, they're the fastest runner. However, that doesn't mean that if you put two high schools next to each other, that one of those two runners isn't going to be faster. In fact, probably one of them will be faster. And then, of course, if you opened it up to all of the high schools in a given city, or if you opened it up to all of the high schools in a given county or even the state, you start expanding more and more that locality, and in a sense, right, it becomes more and more impressive if you are still the fastest runner in a larger locality. So that's the idea of the local maximum and the local minimum. The other idea that I'm going to be talking about with you here is the idea of the global extrema. Okay? In some sense, global extrema make almost more sense in the abstract sense of functions than they do in real life. But we can talk about both as well. So just like local, you can have global max and global min. Okay. And the idea of a global max is that nowhere in the domain are you going to attain a larger value. So f of x has a global max at A if f of A is the largest output achieved anywhere on the domain. So from here, you can have a conversation about, can you have more than one global maximum? This isn't really something we're going to see a ton of. But for example, those of you who find yourself taking trigonometry next semester, you'll come across functions whose graphs look like waves, the sine function and the cosine function. And the conversation might be, well, since it looks like a wave and it keeps coming back to the same highest point and the same lowest point over and over again, does that mean that it has infinitely many global maximums? And that kind of depends on what you want, like whether what you're talking about, it's best to say, you know what, unless it happens exactly once, we don't call it a global maximum, or whether it's better for your purposes to say, you know what, every time it happens, we call it a global max. So the question of whether there can be more than one global max is one that I'm not really going to get into too much. It's not important for what we're talking about. But it is a question, and it is something that you could think about if you wanted. And of course, a global min, same idea as global max, just smallest value. Okay, so those are global extrema. Now, one thing that it is important to point out is that not every function has a global max and a global min, and this is why I presented you with two examples here. So the example on the left, I'm going to use the color scheme that I used here. So for local, we're going to label in black, and for global, we're going to label in purple. So local extrema, well, you have this guy, you have this little guy, and you have this guy. Right? So let's call this A, let's call this B, and let's call this C. So the value at A is a local max, right? So sure enough, if I look at a little window around A, f of A is the highest value the function attains in that area. If I look at a window around B, f of b is the lowest value the function attains in that little locality. And if I look at a little window around C, f of C, so again, we're talking about the y-coordinates of these points, is the highest value that the function attains. So what you're going to notice is when you're talking about local maxes, you're going to see little peaks like this. And when you're talking about local mins is where you see your little valleys, okay? So there's a very visual connection between maximums and minimums and the graph. Okay, so f of a, we have a local max. F of c, we have another local max. And then f of b, we have a local min. Now, let's look on the global side. So the question that is really good to ask yourself when you're approaching this from a visual standpoint is there a highest point on the graph? Like, look at it visually from a holistic standpoint. And in this case, yes, this point right here is the very highest point this graph ever achieves. Never do you see a point on the graph with a larger y-coordinate. So in fact, f of a is also the global max. However, notice that if I were to ask you the question, is there a lowest point on this graph? The answer is no, because the graph continues downward indefinitely. No matter what point you pick on the graph, there's always going to be a point where the y-coordinate is lower. So this is an example of a function that has no global min, but it does have a global max. If we look at the other example that I presented you with here, you absolutely have local max and min values, right? So this, let's call it, I don't know, A, I guess, is going to be the location of our local maximum. And this, let's call it B, that's going to be the location of our local minimum. So G of A, we have a local max. G of B, you have a local min. Okay? Now, by the way, in homework, you're not going to have a ton of homework on this, but in homework you might be asked to list all of the values of x where this function attains local max or local min values. So pay attention to that. Read the problem very carefully. If you're asked for the input where the local max or local min occurs, that's where you would say A or B or C. If you're asked for the value that is the local max value or the local min value, that's where you would say f of A or f of B or f of C. So it's important to read the problem and see what it's asking you. Okay, so G has one local maximum and one local minimum, but notice that it has no global extrema at all. There is no point on this graph that is the highest point, and there is no point on this graph that is the lowest point. No matter what point you pick, the graph extends below that. And no matter what point you pick, the graph extends above that. So this is an example of a function that has a local max and a local min, but it has no global extrema. So we're almost at the end of this lesson. So I just want to add here that there may very well be functions that have multiple local maxes, multiple local mins, but no global max or min to speak of. So there isn't a hard and fast rule that you're always going to have this many, this or that. There could even be a function with no extrema to speak of. A linear example is a good example of that. A linear function's graph is just a line, and there's no peak, there's no valley. So no local max, no local min, no global anything. It's all in the graph. It's all about kind of looking at it holistically, and that concludes this lesson. See you all for the next lesson. Bye.